to look at just machine learning in medical imaging. But I prepare the content for machine learning and deep learning. So very basic level, starting point with some practical one also. So for example, here in machine learning, you have to just look at some image data type and then feature extraction and some data preprocessing. Also some classical machine learning algorithm for supervised and unsupervised learners, and also some evaluation metrics. So the content was covered actually from very basic point of view, and we hope to look at deep learning data, neural networks, and all the deep learning frameworks like AlexNet, LesNet, and so on, with the transport learning. So let's look at machine learning in medical imaging. I think that you first of all saw something like computer vision already, and then some maybe image processing and so on. So now, if we talk about medical imaging, it should be just related to image related to the medical field somehow. So I think basically we need to understand, above the understanding of the image that we have already, we have to understand what is a medical image and what are the types of medical image. So from here, for example, somehow we can have some examples here. Like the first tab is X-ray. I think everybody has done at least one time some kind of X-ray. I gave another example there, like it's used for fracture detection if you have some bone fracture, lung diseases, and so on. Yeah. And also you have the CT image for tumor detection, trauma assessment, and cardiovascular diseases. Another one is the MRI, used for that's the brain and spine, and also some other joints and muscles, disease detection. And also you have to be used to restore pathological images with high resolution, because this is what our laboratory mostly use. This one is high resolution microscopy tissue images. Yeah. So I try to put some example here. You can see. Yeah, so this is some kind of X-ray. Yeah, X-ray, and this is CT image. And you look at MRI here, and this is tissue image. So you can also, in a digital course, like in our case, we study exactly how to, the image acquisition process is important, how to acquire these images from the device, because we need to sometimes do some kind of pre-processing. How it leaves from the laboratory, the hospital, or wherever to reach our laboratory. So we need to understand such type of thing. We can look on your own, but let's look at the structure of a medical image. Yeah, at this point. So we have, for example, here we have image dimensionality. It can be a 2D image, like X-ray and ultrasound. And they present the slides of anatomical structures. It can be 3D. And then they are under many formats now. So we have, for example, the DICOM format, and then you have the JPEG and PNG, and also SVS. So I think actually the SVS format and some other formats are becoming more important, because with the current trend, we want to really go deeply in diagnosis. Yeah, so we manipulate some kind of gigapixel images. That is why it's important to learn about the SVS, what they call whole slide image. That's a format type also. But I think, you know, the Google map, for example, Google map. So if you use a Google map and then you want a specific location, you can see South Korea. As you are zooming, you see Gime and so on until Indian University. But it's this kind of images for medical. So you can see, an image with a size may be normal, but it has the capability to give more detail as you are zooming to a level. And at each level, you must understand the acquisition process, because many things happen there. The magnification, the resolution, and everything that are very important during during analysis. So another parameter you have to look at is resolution and scaling. So image resolution can vary. So it depends, and we know that lower devices sometimes produce image with lower resolution. Yeah, that is why some people buy some bigger phones and so on to get higher resolution. So higher resolution may lead to more details in the image. Yeah, so you can have more details when you have a higher resolution. And then there's also a scaling, processing, and normalization that are important for pre-processing, for example, and then you can use it to ensure that the image can be compressed and compare or analyze across many data sets. So most often while working with these medical images, you can face some challenges, or still, even if you are not a programmer, there are still some tools available that you can use to do some analysis at a basic level. And then I try to cover also some basic pre-processing techniques, for example. So we'll look at them practically very soon. Yeah. So for example, in terms of challenges, you have the high dimensionality and complexity. So like we mentioned about the slide image, they are very big, and then yeah, it makes the manipulation very complex. There can be 3D or 4D images involving very large data. Yeah. For example, we have one image of more than 1 gigabyte, 2 gigabytes sometimes. It becomes very heavy. So it's also very computationally intensive. So it requires a lot of memory and processing speed and so on. Yeah. And then sometimes, because we are dealing with medical images, sometimes because let's assume in the hospital you have a data collection center. So it can be radiologist unit, for example. You cannot decide, assuming you do diagnostics on breast cancer. So you cannot decide that all the patients you have or all the patients you scan will be, for example, positive in breast cancer. So let's assume you have, for example, it can be tumor or normal. So you have to see a medical description, like a benign condition, tumor or normal. And let's assume that you are collecting data. As you are collecting, if a patient comes, what you can do is just collect and what the diagnosis, maybe assign a label. So we assume that you assign the label, maybe tumor, if it's tumor, normal, if it's normal. But you cannot control to say, among 20 patients, I need 10 tumor, 10 normal. No, you are just collecting. So most often after collecting data, there is class imbalance issue. So you will see maybe we have more patients for normal or less patients for tumor and so on. It's not always balanced. And when it's not balanced, it makes our machine learning also problematic. So we need to handle this kind of things in terms of images. And on the other kind of data, there are still some ways that we can use to handle imbalanced data set also. So in this case, we have to look at this aspect carefully because it occurs when they collect data. You will see that in the hospital, you may have 2 classes for a disease and that one class is higher than the other. How do we handle that case? Yeah. And sometimes also, it's hard to get labeled data. It's hard to get labeled data. So basically, if we do image extraction, we need to assign a label. Like, for example, this patch of the image is it, I'm taking this example, is this tumor or is it a normal slide or patch or what? Yeah. So who does that? Just pathologists. He does from experience, so he has to label the data. But we need to know, like, it takes time to do that. It takes so much time, yeah. So it takes time and it's consuming. So you see that for some doctors, it's not easy for them. and now they are very busy. That is why recently you see the current trend in medical imaging is developing techniques that we use data with very limited labeling. This is what research is doing right now. Because they understood already, if you check on all statistics, even in China, in USA, you cannot have doctors that can run this. Yeah, can do all this kind of labeling process. It's very difficult. So what we want is they can do very small amount of labeling, or maybe they can just decide on something, give some insight, and we use that to work. But when I will take an example now, you will see that in this case, we need everything. We need to know, is this tumor, is this normal, for us to do classification. But research now, currently, doesn't need that. They just need to know maybe there is a part of this slide that can be normal, or this person may be likely a tumor or something. So with that, we can use. So whenever you acquire the data, there are some tools that you can use, for example, to first of all run and see how it looks like. Yeah, for example, you have in our laboratory we use this one for whole slide images, the QPAT. Yeah, for very big size images. So you can open an image and then you are able, because if you open with QPAT, the pathologist is able to do annotation. Annotating means he can show a part of something. This is an example. This thing, you can call it a slide. We'll give many names. We call it a slide. Another person may call it a patch, but it depends on, I can say just the size. Yeah. So most often when it's small, you can call it a patch. Yeah. So in this case, this software, you know, our responsibility is to make some models that will be able to predict. That is our main goal. We make models that will be able to predict, but in this case, we assume maybe somebody that is not computer, you just want to see the image and see, because actually there are some images on which you can see clearly that there is maybe some cancer or something. It shows with eye. You can see some red color or something like that. Yeah, if you want to visualize the image, you can use one of these tools. And these tools are also used in some cases for annotation. So one example is, if in this case, they can come and do a little annotation here. It means on this slide, this side will be considered as tumor, for example. This is an example of annotation. So you can use this kind of tools to view the images. And then you know the normal JPEG image in your computer, like you double click and then Windows opens. That is also one. Because some images are on the JPEG format. So that one you can open and view immediately. And then the other ones that are a little complicated, you can use these tools to view them. You must not always view in the programming environment, no. You can also view the image before having a view of what it is. Yeah. But each time you work on medical imaging, you need to think about a public medical data set. But I think you know what is a data set is, just a set of data, like it's explained basically. And then, actually, medical imaging is a little tricky because it has to deal with human parameters, and so it's very sensitive. In this case, you must have some authorization if you want to do some proper research about medical imaging. So sometimes, if you want to avoid that kind of situation, you can use publicly available medical data set. It's good, it's important to know, like some famous ones, like the Camellion, you have 16 and 17 TCGA, and then you have that long data set. And there are many of them online, so you can have on Kaggle repository or some specific website for those diseases. So it's very important to get public images, because sometimes private images are very sensitive. You are limited, you cannot use carelessly. If not, you may have some ethics issue. Yeah. So it's important to know exactly where to get some of these images. Once you acquire the image, you need some kind of pre-processing are required, some just basic operation you need to do, generally cleaning the data and preparing the data for for using it in machine learning. So I just try to cite some few basic preprocessing techniques here, like the normalization. Yeah, in this case you are trying to involve scaling image intensity value, yeah, at a constant range, for example, and then you have cropping and resizing, assuming that you have some images that are not on the same size. Yeah, you can adjust the image to have maybe the same size, yeah, and then also try to fit it into the machine learning model if you're trying to get a solution. Yeah, and for example, in this case, where we have limited data, for example, we can use some kind of upsampling or balancing method, I would call it that. Yeah, so one of the methods is data augmentation, for example. So data augmentation is all about you have to take existing images and try to make more images to balance the data set. Assuming in a setting you receive like maybe few more, let's say 40, and here maybe 10. There will be a little bias to train a model with this kind of data. So sometimes you can do augmentation on the similar data set. And the kind of operation you can do some rotation. Because the same image, you can do some rotation. So you take the distance and the angle, for example. You can do flipping, zooming, yeah. And then you try to increase maybe the size of the data set artificially from what you have before. So these are one of the techniques. You can create, for example, 30 more images. Artificial images, like fake images, but with the same properties, to train the model in a balanced way. Okay. So once you have succeeded to, once you've succeeded to pre-process the data, like making the data clean and ready for treatment, one of the stages you can do is to extract the features. Yeah, because what we see is an image. We see an image like a photo, but the computer doesn't understand that way. So we have to remove certain properties from that picture that we are going to judge the image from it. Yeah, we have to remove some properties, and those properties is, we refer it as features. Yeah, so there is a process, a very key process, as a feature extraction process. Yeah, so actually you have to do feature extraction, for example, to reduce the dimensionality. Yeah, so you have to focus on the most relevant information in the image. I want to take an example, just a very simple example. I'm still here on the whole slide image, or some slide image, for example. So, and this is my image. One of the properties of this image, for example, can be the area of this image, it can be the perimeter, or something. Yeah. So if I have another image, I can have that property. But there are many things on the image, like this space. I don't know exactly what it is. And this other space, I don't know the size and so on. There are some irrelevant information here. So the feature selection process means I will use this one to get most important properties. How can I get the property? Because after all, machine doesn't understand this. Everybody knows machine understands those figures, 1 and 0, and so on. Yeah, so from this image, I have to extract features, meaningful features. Yeah. So once you do that, you are reducing the dimensionality. So it means the complexity reduces, and then you focus on what is important, and then you can increase the interpretability. Why? Because, for example, I'm able to know that the area of this image is like this, the perimeter is like, so I understand better. I can say this image is bigger than this, or so I can compare, I can see something according to the image shape. So it makes interpretability more easy. And then, in this case, there are many things you can do. For example, you can focus on the texture, you can focus on the structure, on intensity, variation, and so on. Yeah, to get the features. But we have to try to do some in practice. Yeah. So let's look, for example, at some type of feature extraction processes. Yeah. in terms of feature extraction processes, you will see that I mentioned shortly that we will not cover deep learning, for example, but so this feature extraction, they are oriented towards machine learning. So we have to differentiate very well. AI, what is AI, what is machine learning, what is deep learning. Yeah. And then these feature extractors are oriented towards machine learning. And because deep learning, they are different. So in this case, for example, one of the features, like, look at the feature as a property. So one of the properties of an image can be the intensity-based feature. In this case, you look at the pixel intensity values. You know it varies from 0 to 255, the brightness of a pixel. Yeah, so we can get that as a feature, as a property of an image. So if we get it on one image, what can we do? For example, we can evaluate the mean, the standard deviation, the maximum, the minimum, and so on. Yeah, because if you extract the values, you can therefore have the mean. I hope you see the one image like this, what they say 40 by 40 is so big also. So you don't claim to know how one pixel, no, it's impossible. So you have the 40 by 40, for example, and then you can extract the pixel intensity, and from all the pixel intensity for each pixel, you can find the mean value, you can find the average value, you can find the maximum value and the minimum value. These are the properties of this image. These are the properties of this image. You have to extract these values and it is attached to this particular image. And if you have another patient with another image, you extract, it gives its own property. That is what we call features. Another very important feature extraction method is the texture feature extraction, the texture. Yeah, texture, then we have the DLCM. Yeah, the DLCM algorithm. That is a case study we have to look at today. And a local binary pattern. Yeah, and there are many. So I refer to one library, you get it in the assignment. Yeah, where you can get many other texture extraction methods. Yeah. So DLCM is used to calculate many things. Some kind of feature like energy, correlation, dissimulation, similarity. So we'll see it very soon. And then you can also focus on the shape and morphological features. The shape and morphological features, we look at the shape, we look at the size, we look at the structure. For example, the area, the perimeter, the eccentricity, the circularity, the compactness, and so on. Yeah, these are some features that you can extract from an image. And also the frequency-based feature. You can use a Fourier transform, you can use Laplace, and then also the wavelet to extract features. Standard equations as you know. Other features, you see the edge contour features and histogram base and so on. So there are many. You can look for more. Once you have extracted the features, let's assume in a case where we applied maybe 1, 2, 3, 4 feature extraction, so we have a certain number of features, and once it's extracted, there is what we call sometimes a feature selection. Because we said when we do the feature extraction, we're already reducing the dimensionality. So we take from high dimension to low dimension, but still, all what we extracted must not be relevant. So we have to check, is it relevant to our algorithm or so on? Yeah, so an example, what you can do here is that you have to do a feature selection process. It doesn't, it's not important to make, we need to be rational in the way we use memory, for example. So you don't need to train a model with unnecessary features. You just make computation high for nothing. We need to be very rational. So we use the smallest memory for the task. And it should be done perfectly. So if there are some features that seems to be unnecessary, it's good to remove them. If not, the model will be complex, it takes much time and so on for training and testing equally. And we find ourselves in a situation where a patient will come to the hospital and stay for 2 days, 3 days, just to wait for maybe a diagnosis or something. So it's good to always select features when you can. Like for example, here, you can select the most relevant features from a larger set. So if we've extracted more than 200, 500, 1,000, 1 million and so on features, we can select most important. And it's also important because it reduces overfitting. So you have to learn about model overfitting. And you see that one of the ways to avoid overfitting is by performing proper feature extraction. So some common methods that we use for that is a correlation-based selection, the wrapper method. So for example, I think this is one of the famous also, recursive features elimination, machine learning. Yeah. Because in this case, you can classify features according to their importance. Like, I have 100 features, which one is more important from year to year? You have to classify, and then sometimes you may not be able in medical imaging, because in computer vision and other applications, sometimes you decide, I will use this number of features. But in medical imaging, sometimes you cannot, because you need pathologist advice. What if you remove a feature that is really important in diagnosis? The pathology has to tell you, no, this feature is key. That is why we always communicate to know what they want and so on. But in a normal case, you can extract feature and run your selection and just do the classification. But in some cases, you have to, in medical imaging, it's a little complex. It's better to seek for pathologist advice for professional solution. So another way for feature selection, dimensionality reduction. Yeah, like in this case, we have the PCA, principal component analysis. This is always used mostly in the unsupervised learning, that reduces dimensionality by projecting the feature onto a lower dimensionality space, returning the most variant in the data. So in this case, when we study unsupervised learning, we always use most of the PCA and Canon algorithms and so on. So you have the U-map for adjusting image size to fit the model. And also data augmentation technique that you can use for nonlinear dimensionality to reduce techniques for visualizing high dimensional features. So let's go into the classical machine learning. I know some very big programmers will see it as basic, but it's very important for freshmen. Very important at this point. So machine learning, first of all, machine learning algorithms. So let's look at it like kind of, they used to automate some process, but in this case, machine learning, they learn from the data. They learn from the data that you have, and they try to do one thing. In general, we can call it prediction. What machine learning does is prediction, but what kind of prediction you need to know. So in medical imaging, you have image classification, you have segmentation and diagnosis, for example, detection. So I will show some kind of example of what it is. It's important to understand what is classification, what is segmentation, what is diagnosis, and detection, or so on. So if you heard about deep learning before, you see that in deep learning, features have been extracted automatically from raw data. And there have been thousands and millions of features from the raw data. But machine learning is not like that, so it has to rely on extracted features. You need to extract the features first before you can apply. Now, supervised or unsupervised learning for the classification. But you can have a look at this. Like here, you have machine learning. You have like classical machine learning and modern machine learning. So classical machine learning can be used in classification tasks and regression. So I will give example difference between these two, and these are some examples of algorithm. The most famous sometimes is supposed vector machine and then decision tree. And modern machine learning, you have neural networks that goes into all the deep learning. So the paradigm is really different. Sometimes I think it depends on how you define it. Some people will say AI, machine learning, deep learning. Some other people will say in AI, we have deep learning, machine learning, and some kind of thing. So it depends on the literature, the journal, and everything, how they define it. Some authors, But in our case, we look at machine learning separately from deep learning. So we look at AI, like machine learning one side and deep learning. So let's try to understand what is regression. what is regression, for example, and what is classification. Because we say the overall goal of a model is to perform prediction. So prediction can be classification, segmentation, and so on. Yeah, so what is, for example, classification? And here, we try to say classification, classical machine learning helps for classification and regression. So we need to understand what's the difference between them. In terms of regression, so we can predict a discrete value. For example, what could be your age? So you just answer 25. This is regression. It gives an integer value, for example. And then, when in classification, we say you can predict a continuous value as a class of labeled probability. So they will say, like, are you an adult or a teenager? So you answer adult. It doesn't give specific about the value. You see, in regression, you have the exact value, but in classification, you give a range, a class, or something, a probability to belong to a class. Yeah. So it's very important to differentiate between the two to know exactly what type. If you have an assignment, know exactly, am I going to apply classification or regression? It's very important. And also, segmentation. What is segmentation? It means that you partition an image into distinct region or object of interest. So, like, for example, you can partition the organs according to some classes or maybe some pathological regions, for example. So when they talk about region, I think you can see in medical imaging what is a region, but you have to know this region, object of interest or region of interest is important. That it shows that we focus on it in a simple way. It's very important. So we always call ROI, region of interest. So there's a focus on the region of interest, and then it has to show something specific. Okay. What is detection? Detection means you are identifying and locating a specific anomaly. So you detect the object, the region of interest, within an image. So let's take this MRI image, for example, and then try to see all it. So in a classification task, in a simple way, I can say this is tumor or normal. This is classification. And then in detection, you see I have a bounding box here. It shows the tumor area in this case. And then in instance segmentation, it shows exactly the location, and then you have semantic segmentation that shows the location within the whole, with the different classes or, yeah. So you have 1, 2, 3 in semantic, and then here you have the exact region of interest, and here you have the bounding box that shows the detection. So let's have another look at classical machine learning, because we try to talk about it. And then in classical machine learning algorithm, you have to know that there are at least 2 paradigms that you need to follow. Yeah, because think about the data that you have at hand. We are still on medical imaging. So I receive some medical images and I want to maybe classify them using classical machine learning algorithm. When I say classify, you now understand. It means I want to define if it's a tumor or normal or something. Yeah. So in this case, I need to check the data that I receive, are they labeled or not? Because the paradigm is very important. So in classical machine learning, you have to data pre-categorization or numerical. You need to know, do you have some, do they belong to specific category? This data belonging to this category? Are they normal? Are they tumor? Are they, I don't know. Yeah. And then the other side, it doesn't have any label. They just gave you some images, no label. They just say this is liver image. You don't know if it's normal or not. So if you have some labels, if you have some pre-categorization, you can call it supervised learning. And in the other case, you call unsupervised. According to the data that you receive, after data acquisition process, you can define, am I going to use supervised learning or unsupervised? It depends on the data. Are these data belonging to some category? Are they belonging or not? So you have to think about that kind of situation to know if you have to use a supervised or not. And then, in case of supervised learning, you think about it. Are you predicting a category? if you do category prediction, is it tumor, is it normal, is it, I don't know, anything, any class, then you are doing some classification. Yeah, like for example, this is an example here, yeah, of classification here. But if you are predicting a number or a value, a specific value, in that case you are doing a regression, yeah, you are doing some kind of regression. And then in case of unsupervised learning, you have at least some things that are happening, like you have to take the whole data and try to do some clusters. First thing, clustering means you have a whole data set and then you try to categorize them kind of similarity. Those that are looking alike, yeah, you can put them in terms of clusters. So, like for example, here you split up similar clothing in a stack, yeah. So it makes a clustering, and also you can, if you are able to identify some sequences, it can be an association that you find what cloth of, yeah, can wear together, for example, what kind of combination can happen. But in all the cases, you don't have any label. You are just trying to make some group. Yeah. And also you can use dimensionality reduction, like PCA, just so. Okay. Let's look at this now. Let's assume you have, you are asked to prepare a model for prediction. So I think if we need to use our terms very well. I want to prepare a model for prediction. And in that prediction, I need to think, is it classification, regression, and those kind of things. So let's assume in this case, we want to develop a model for predictions. It means I want to do classification or regression in a problem. Yeah. So this is the hospital, and this is a patient that you can see. The first thing is that you must acquire data. You must have data. And the primary data collection processor. In our case, we can get on maybe Kaggle repository and many others. Yeah, but in some cases, we communicate directly with hospital, so you must acquire data from patient and from hospital. Yeah, so the patient gives data to the hospital, they make a data set, and they send it now to the machine learning engineers, for example. The first thing that you have to do once you acquire the data is to prepare the data, making the data clean and ready for preprocessing. So some kind of things you can do inside is data normalization, data cleaning, data reduction, data extraction, selection, and so on. So because sometimes when they come, they are really scattered. You need to do a lot of operation to make them available to, able to understand, and then also they are used. In this case, you have to, if you've prepared the data already, you have to construct a predictive model. So a predictive model, sometimes you need to choose the best classifier. And you see that classifier, you may be confused on how to choose, because sometimes you have to try and see how the result is coming to evaluate. So you cannot say, for gastric cancer, this classifier is always performing. It's not a law. It goes like that for even deep learning and so on. Yeah, so you cannot always say this is effective than others. Sometimes you have to try somehow. So we already tried with transformers that are also recent to see that it's difficult to just decide that for this kind of image I can use this kind of model. No, sometimes you have to try a little more. Yeah. So yeah, at the level of constructing the predictive model, so the model you have to look for the classifier selection. You also need to give some parameters and hyperparameters tuning. Then you do the training. After the training, you can evaluate the classifier. Evaluating means like how is it performing? So there are some things you have to know about how it is, and then you can use it for prediction. Prediction means before I use this data from the hospital, I try to prepare everything, and then I can do evaluation. It's good. So next time a new patient comes to the hospital, he uses this model, the best trained model, because there were many models here, we use the best model. So we take his data, we put inside the system, and we get some output here. It can be maybe, if we maintain this case tumor or normal, I collected data before, I did the training, and then Later, a new patient comes, he gives the data, and then we try to predict now. So in this case, we are doing diagnosis. Okay, so let's try to look at some typical classical machine learning algorithms. I will just have to look at 5. There are many. Yeah. So the first machine learning algorithm is a support vector machine. And you have an image here already that shows some kind of things about support vector machine. So support vector machine is a powerful supervised learning algorithm. When it's a supervised, it means that for you to use it, you must have some labels, or your data must belong to some category. You must know the category or which your data belongs to, or else you cannot. So it's used for both classification and regression. So you can use to classify a category or a value, for example. Yeah, so the way it works is that it's finding the hyperplane that best separates the data point of different classes with the maximum merging. So for nonlinear separable data, support vector use the kernel function. Linear, it means it's a straight line. So in this case, you have, for example, this is the decision boundary, and then these are the support vectors nearby. So this is one class, and this is another class. So you have the hyperplane for the first class. This way, it can be tumor, for example, and there you have the cancer, the normal, for example. So how does it work, the support vector machine? What it does is that it identifies the hyperplane that maximizes the margin between the closest data points. Yeah, so for one class, A and B, they try to maximize and identify the hyperplane that will separate them. Yeah, and then in the case of nonlinear means you have a you don't have a straight linear function y equals to ax. In that case, you need to use a kernel. Yeah, so the kernel allows the support vector to handle nonlinear data by transforming it into higher dimensional space. So in practice, I think we'll see some parameters that you can use here to define if you have to use kernel or not. Yeah. How do we use support vector machine in medical imaging? For example, you can use it for classifying medical imaging based on extracted features. And you remember the feature extraction process. So if you extract features, you can use them to do classification. And then you can use in detecting anomalies in X-ray, for example, or CT scans. Yeah. So they are actually good for binary classification. What is binary classification? It's a kind of problem where you only have two classes on which you have to do prediction. Just two classes, binary. And then the other one, if you have more than two classes, you can just call it a multi-class classification. So what is good about the support vector machine is that it's well in high dimensional spaces, and it's also effective for small and medium data sets. So if your data set is not too big, it's important to use it. You have some good performance, and that you can also handle complex decision boundaries with the use of kernels. But the limitation also is that it's difficult to choose the right kernel, for example, and also sensitive to hyper parameters. Yeah. So like here we have the gamma coefficient and then the C. So we will see some hyper parameters in practice. So these are some kind of things you can manipulate, and in this case, we focus just on the images. But in most cases, why not? In some assignment, you will be asked to combine like you can combine patient history, for example. It's weight, it's height, and everything, and some other gene expression. They may not be image data, but you can combine with image data to make more informed decision. Let's look at another class of classical machine learning algorithm. This time we want to look at decision tree and random forest. Decision tree and random forest. So the decision tree, for example, at this point, decision tree, you look at it like this. This is a very simple example. Decision tree. You ask the question, should I accept the new job offer? So you are here, and then you have some decision nodes. Like here, the salary should be at least $500. So you have, at this point, you can take a decision. If it's no, then you decline the offer. If it's yes, you have to another condition again. Like for example, commit more than 1 hour. Yes, decline the offer. So if it's the condition not satisfied and so it's just like a binary kind of thing. And all these things are called leave. And at the end of the day, this is what you have, the condition accepted. So at each level, at this level, there's a classification, at the next level there's a classification, and here a classification until we arrive to both classes, like accepting the offer or declining the offer. So this is a decision tree, for example, and then the random forest is instead where there are many decision trees. Yeah, so it's a combination of many decision trees. This is a typical example. You have some instances here, and then you want to do some kind of classification. So you have this, you start from here, and then you do classification, it gives this. This is one decision tree. It gave the apple. This another one gave the apple, and this one gave banana, for example. So what happens in the random forest? In the random forest, there's a process here that they call the voting process. It can be majority, average, and so on. You can define, or it's defined by default. Which one do we choose? Like in this case, it's majority voting. Majority voting, like in this case, among these three classes, it's the apple class that is dominating. So classify this as apple. But there are many decision trees actually. What are the applications in medical imaging? In medical imaging, you can use it for classification of images and patches by learning decision rules. You know decision rules. Decision rules are very basic. That is what every logistician used before. Yeah, if, yes, no, and so on, until you have the final result. But today, we went to another paradigm where we don't go on logics again. Based on data, we learn from data to get decisions now. So, and this decision tree focuses also on that kind of logic-based system. So you can use it in case of maybe disease detection, for example, the long readers. You have many people have used it already. You can check in the literature for detection of lung diseases. And then breast cancer also. There are some people use decision tree and random forest like that for classification of mammograms and analysis and detection of diseases. Yeah. So what's the advantage of this? Decision tree are interpretable because most of the time you will see in the new paradigm, you will see that people have some difficulty understanding. That's what we call machine learning models a black box model. So we want to add explainability. How to understand the decision? How do we understand? Why is the model choosing this one like this? You see that with the decision tree, it's a little easy for you to see like, it's choosing because at this point it was classified as apple and then there were two apples on top of also he voted for that one. So it gives a little bit of insight about explainability, which is also very important to give to help the medical doctor to interpret and be sure of the kind of results. Yeah. And then also the random forest improve the accuracy because obviously the random forest, it does what we do here one time. What we do here one time, it does many things, so it is more effective. So some kind of limitation is that in case of small data set, there may be overfitting, so the model may not operate normally, and then random forest may lose interpretability and tuning in terms of many trees. So when the trees and the leaves are really many, it becomes very challenging to understand. So let's look at another algorithm here, the logistic regression. So the logistic regression is a statistical model used for binary classification. Yeah, so the model's probability is a binary outcome. So in case like a presence or absence of a disease, for example, disease detection or classification. So application is that you can use for disease detection and also liaison detection. The strengths are well defined and also the limitations. But in all the cases, the logistics You see, in this thing regression, you have the sinus function sigmoid. Yeah, sigmoid function. So because in this case you can have a linear regression or a logistic regression. So logistic regression goes to sigma or the log function, and this one goes on the straight line for the different kind of classification. Another example is knife Bayes. Knife Bayes is a probabilistic algorithm that is used on the Bayes theorem. I think that everybody has seen this in other gadgets, something like that. What is the probability of A depending on B? Yeah, so the probability of A being that given that B is true. Yeah. So if B is true, what's probability of A generally? Probability of B if A is true, multiply the probability of A all over probability of B. Yeah, so you need to understand this works exactly in that principle, and you can see here how we used to classify. So you have the probability A and B become the class and the data. The class and the data, and you see exactly how it happened for the classification. So we're meeting in 10 minutes in the data set, for example. Okay, we discussed already about supervised learning. So this time we want to look at one unsupervised learning, classical machine learning algorithm. So most famous is K-means algorithm or K-means clustering. So it's an unsupervised machine learning used for data clustering. So unsupervised means that the data that you use for training is not having any label. So it doesn't belong to any category. You have a whole data set without category. And then you have to partition it into K clusters. Cluster means like groups. You have to make it in K groups of feature similarity. So they should have same properties in various groups. Yeah. In that case, you can minimize the cluster variance, because as you are minimizing, you are making less groups and more classification. You can get an example here. This is a data set before the K-means. So you have this data, and then after the K-means, you have one group here, one group here, and one group here. So they make some clusters. They call it like that. And then it's good because this algorithm is particularly good because it's simple and fast. And then, yeah, it can also work well on large data sets because you change the number of clusters you want, the K. Once a K, it can be 2 clusters, 3, 4, 5, and so on. So you can change, and then the limitation is that it's sensitive to the cluster number. So if you fail to put the correct number of cluster, it's very sensitive. If you put 2 or 3, yeah, the classification will be done according to the number of clusters you want. And sometimes you can be confused to know if you have to repartition this data into 2 or 3 or 4 classes, for example. Because it's unlabeled. So how do you put it? It depends. Yeah. And sometimes you have, because you need to choose manually the number of classes, so you need to set the number of clusters K in this case. Once you have used this classification model, it's important to do some kind of evaluation. Evaluate what you want to think. You want to look at this time. So exactly, you have to evaluate the performance of a model, yeah, involving the range of metrics, yeah, to know how the prediction is being done. Is it trustworthy? Because having a model doesn't mean you have base accuracy. It means already the model is good. No, you have to look at many things. Because we mentioned overfitting. If you look carefully, you see that you can have some results that are not good, yeah, or very high accuracy, but it doesn't help in anything. So it's good to understand how to evaluate a model. So one of the things, one way to evaluate, or one of the metrics, is the accuracy. And evaluation depends on the task. If it's classification, there is a way. If it's segmentation, there is a way. If it's detection, there is a way. If it's many ways. There are many metrics. Yeah. So let's look at the classification. So that's why I say classification model evaluation metrics, just classification. Yeah. So for example, here we look at the first classification is accuracy. So when you look, accuracy means I have 100 data. How many did I classify correctly? This kind of thing. How many? So if I classify maybe 95, it means I have like 95% accuracy. You understand that the more is well plus the accuracy is high, the more the model is supposed to be good. I can't say good. It's supposed to be good. Because in some cases you can have high accuracy, but it doesn't matter. Yeah. So if you want to perform accuracy, you have to compute it this way. But in practice, there are some libraries already that helps to do it. So it means you have to look at the true positive. And what is a true positive? Let's take this example again. We have two classes, tumor and normal. And then the true positive means that the model correctly detects a tumor as a tumor. You wanted to do tumor classification, and then you detect it as tumor. This is tumor, and you detect it as tumor. So this is true positive. That is okay, the best case. And you have another case which is true negative. True negative means the model correctly identifies no tumor when there is no tumor. It means it detects the other class. It says, this is normal slide, and they said it's normal. That is okay also. But look at this case now, where you have the false positive. It's a wrong signal. It's a wrong signal. So the false positive, the model incorrectly detects a tumor. It gives a false alarm because this is not tumor. It's a normal slide, but it detects as tumor. This is false positive. It says this thing belongs to this class when it's not. And then the false negative, it means it's already normal, but it still detects as normal. Yeah, it fails to detect as normal. So in this case, the model fails to detect a tumor when a tumor is present. So it misses the diagnosis totally. So you can understand that so far as you have a if you are able to do very good accuracy, it's supposed to be very good. You have good accuracy, model goes well, but in some cases you will see that the accuracy may be biased because of your data and some things. That is why we say good accuracy is supposed to say good model, higher accuracy. So you can evaluate it. If you evaluate this, it will give from 0 to 1 the value, or you can have the percentage from 1 to 100%. And another matrix is the prediction, the precision. So it just measures the proportion of correctly predicted for the positive cases out of all the cases. And also, you have the recall and F1 score. Yeah. And then some other accuracies, some other metrics here is the region, the area under the AUC. The AUC. So this one, for example, will give you another matrix on how the model performs. So let's look, for example, this way. You have a stretch pole here, and this is a model. So this way, this is a curve here. So this is a false positive rate and a true positive rate here. And here you have the best classifier this way. This is a training curve, so it goes like this. In this case, you have a random classifier, 50-50. So it makes no difference, but in this case, you see it's going up a little on top of this and this and this. So in this case, this one is the more better, and it gives the very best. And another metric is the confusion matrix. So in the confusion matrix, we actually give the information about the true positive, true negative, false positive, and false negative case. So it helps you visualize it and distinguish between classes. So in this case, you have the matrix like this. So they will actually tell you this is what we had and this is what was predicted. So it was negative here. Like you have positive. To have this, you have positive and positive. This true positive is okay. And here you also have negative, negative. So because the actual label is the same like the predicted, so it's okay. In this case, you have these values. And there's case of misclassification where you have a negative slide that gave a positive prediction, which is not good. So it's a misclassification and it's similarly also misclassification. But the confusion matrix is good because it gives very visualized insight about it. Take this example, they classify benign and malignant cells, for example. So this is a confusion matrix. You see that you can make it, somebody can easily understand, you can see in this case that you have this benign class. The actual values here is benign and it's also predicted as benign. So 88 cases in this data set. And here you have malignant, 52 cases. So you have here the good classification, and you have some cases of misclassification. Like here, you have the malignant, actual value of malignant that was predicted as benign, just one. And you have an actual value of benign that was predicted as malignant, 2 here. So it shows the 3 misclassifications in this case. And it's very fast to understand confusion